Good evening and welcome to tonight's Suffolk webinar. We have Jeremy Jeske, who is the USSA president, and Dr. Joe Emenheiser, extension specialist at UConn, as well as a USSA member, here to talk with us about Suffolk trait heritability and some breeding strategies. With any of you who are joining us via Zoom, if you have questions, please feel free to send those through the chat or question and answer section in Zoom, and I will share those with our speakers. If you're on Facebook, feel free to share those in the comments, and I will feed the questions to them as well. With that, I'll let you guys go ahead and get started.
Good evening. Thanks for everybody for joining in. Bear with me just a second while I try to get my slide advancer to work. And if not, we'll just rock and roll without it. So I'm Joe Emenheiser. Jeremy's going to be jumping in. We'll alternate through here. The goal is to leave plenty of room at the end for questions and answers. So if you have questions that come up, put them in the chat and we'll deal with them at the end. I always like to start these presentations with a talk about natural selection and thinking about populations of animals, which in reality is what we're doing with the Suffolk breed. And so most people are familiar with the concept of survival of the fittest in a natural population or a wild population. And from a population standpoint, the fittest population is that which is most adaptable to change. The environment that populations are subjected to is constantly evolving, and so a population needs to be able to adapt to that to be able to continue to survive and reproduce. And so that adaptability often comes from variation, and that's going to be a common theme throughout the night. Variation is the body that selection, whether it's natural selection or artificial selection that we'll talk about shortly, acts on. Selection acts on variation, and variation keeps a population responsive to change. And as a result of that, most fitness traits that are related to survival and reproduction have an advantage for a heterozygote, which means that it has a diversity of genes. This is a very simple example of color in soy sheep, not necessarily an immediately obvious survival trait, but one that there is considerable variation in a wild population. If something were to evolve with, the shade of the trees or the brush that they sheltered in, and one was able to be more camouflaged than another, selection would favor that genetic variation. And so that's really exactly what we're doing throughout the rest of the talk tonight. Sheep were originally domesticated for a purpose. Those purposes were multifaceted, evolved over time with society. But basically, all domestic sheep today descend from the wild mouflon. They range considerably visually, phenotypically, genetically. At this point, from the merino, which has the finest fleece in the world, to a Beltex, which is extremely heavy muscled. Very different genetics, within those populations, but they've all descended from the same source and just a result of selection for those specific genetics that result in a specific purpose. And so along with that purpose and that value for the purpose is a concept called consistency. And anytime we talk about a quality product, it's necessary for that product to be reliable, to be consistent from one time to the next. Not necessarily saying that all markets demand the exact same type of lamb. I certainly understand that that's not the case. But within a product, within a brand, it's important that product is uniform from one purchasing or eating opportunity to the next. And so that selection for consistency, again, by design, is a reduction in genetic variation. And that's really what we're going to be talking about for the purpose or for the rest of the night. Ruminants are extensively managed. You know, as a ruminant, they have microbes in the rumen that break down structural carbohydrates in forage, particularly cellulose. Essentially, their purpose is to convert things that we're not able to convert into things that we can. And so because of that extensive management that's very land-based, many times we have more opportunity to control the genetic piece than we do the environment. We certainly have more opportunity to control genetics than the climate and the weather that we're subjected to. And we control genetics with basically two strategies that we'll talk about tonight. One is selection and the other is mating systems. Basically, selection is who stays and who goes, and mating systems is who gets to breed with whom. So within a random sheep population, and I fully recognize that these are not Suffolks, you know, there are going to be some that stand out. And our goal of selection is to move the population in one direction or another, depending what our goals are, depending what we're trying to produce. And so essentially what we're doing again is manipulating that variation, identifying which animals are different, and then determining whether that's a good or a bad thing, whether they should be called or whether those are the stud rams that we breed from. And so that's ultimately our decision point every time is, you know, do I stay or do I go? Populations for any of a number of traits, regardless of what it is, however we measure it, generally align themselves with a normal distribution or a bell curve that most people are at least marginally familiar with. Our goal is to remove the sheep that are poor performers or keep us from achieving our goals. Remove them from the population, select from the ones that are working for us. Ideally, you know, select intensely for the ones that are really working for us, and move that entire you know, bell curve, which represents the population, in a desired direction. Now, depending on the trait, that might be positive, it might be negative, and it might be a combination of those things for multiple traits. But the bottom line is, if you can measure it and if it's variable, you can change it, and that's largely what we're focused on here tonight. So a schematic from the Sheep Production Handbook, which is a great resource from ASI if you're not familiar with it. Again, the bell curve. On the y-axis, we've got the number of sheep, essentially the frequency. And what we're observing here is that most sheep, regardless of the trait, are going to have performance near the average. There'll be some that have extremely low performance, some that have high performance. And I say performance, but this could be really any trait. You know, it could be their height, it could be their weight, it could be the shape of their ears. Certainly, you know, the more quantitative that trait is in nature, the more likely it is to be normally distributed. But consider this essentially applicable to all traits. And so our goal within the Suffolk breed and within our flock, we've got you know, our breed standard. We've also got a goal for breed improvement. And within a flock, we've got a goal for flock improvement, whatever those criteria may be. Relative to that population, relative to those goals, we are trying to shift our bell curve, so to speak, in a desired direction. Jeremy, I have a note here.
Yeah, I was going to add a couple things here. Joe's kind of touched on this already, but really, you know, Kyle, I kind of look at this as you're really measuring those individuals that you think are outstanding for whatever trait, or more towards the high end of the curve, for example, compared to the average of your flock. And I also wanted, even though we're going to talk more about NSIP later, this bell curve is really important, and I want to kind of use it to sort of dispel a misconception that I hear once in a while from folks who maybe question whether or not folks who are in NSIP are reporting all their data, or they only report data on the good animals. Well, the reason why you don't do that, and the reason why you need to report data on all your animals, is really what that's measuring is the difference between an individual and the average of your flock. So if you take all your low performing animals and you don't even report data on them, the program doesn't know they exist, and it makes a new bell curve for you for your flock on the ones you just report, and it essentially brings your top animals down closer to average because they're not compared to those poor ones. And so we'll touch a lot more on that kind of later, but I think the structure of this bell curve is important in terms of how we, why we select the high performing, how important it is to select those that are significantly better than average for those traits that we're trying to improve. So
absolutely right. Yep. No matter what your flock, no matter what your goals, you're never going to have more than, or you're seldom going to have more than half of them above average. Right. It's just how it goes. Everything is relative. And so with those goals in mind, kind of working through some genetic principles to understand these things. When we visually evaluate sheep, one of our misconceptions is that we are evaluating 100% genetics, and we give a lot of credit to breeders, and if an animal wins a show, we recognize the breeder of that, and certainly breeding is very important in producing, a quality show animal, quality performance animal, whatever the case may be. But one thing that I'd like to emphasize tonight, which is going to segue into our talk about heritability, is that phenotype, whether it's what we see or what we measure, phenotype is a combination of genotype and environment. Genotype essentially includes genetics. We'll break that down a little bit more. Environment are the factors that pertain to how that sheep is managed, the weather, so on and so forth. We might also loosely hear this referred to as nature and nurture, where nature is the genetic component and nurture is the environmental component. But phenotype is a combination of genotype and environment. We take that environment piece, we can partition that into climate or the weather, and also management, nutrition, seasonality, that sort of thing. Essentially, there are environmental factors that we can control, and there are many environmental factors that we cannot control. And parse those out a little bit. But generally, many people's breeding strategies is to take the best, breed them to the best animals, and hope for the best. And so the difference from one breeding program to the other, that ideal might differ. But the difference in strategies really comes down to how well a person defines what is best. And one of the biggest pitfalls that we can run into is selecting for things that really are environmentally controlled and misattributing them to genetics. It can lead us down the wrong path simply by selecting for things that are not replicable. Jeremy?
Yeah, and I just to build on that a little bit, I created this graphic just to kind of show that, we're going to talk about heritabilities of different traits here coming up, but just to kind of preface that, even the traits that we think of as being moderate to highly heritable, or the highest heritable of these traits, you're talking about 35 to 45% heritability. So what that means is 55 to 65 or more percent of what you see or what you measure is due to environmental factors. So more than half of what we see and measure is caused by environment. And genetics are passed on to offspring, but environment is not. And so that's the reason why, if we rely solely on visual appraisal, we fail so often in our matings, is because, as Joe mentioned, there's a lot of environmental influences, primarily nutrition and health, but also birth type, rearing type, age of dam, and all of those things go into which lambs had the best environment to grow and produce compared to others. And so we'll touch more on that as we get into some of the heritability stuff.
So to break this down a little bit further, to get us through this introductory breeding section, starting with phenotype equals genotype plus environment. We broke down the environment piece, essentially things that we can manage like nutrition and health, things that we cannot manage like severe weather events or so forth. That genotype piece also can be broken down as well. And again, without getting too wordy or too textbooky, essentially the genotype piece can be broken into additive genetics and gene combination values. Now, those two terms may mean nothing to you right now, and we'll try to break it down a little bit more. Very, very much an oversimplification, but if we think of a gene or we think of a trait being controlled by a set of genes, and again, this is simply inherited, not all traits, very few traits are this simple. But at that particular locus or location in the genome, there are two alleles, and one of those comes from the sire and the other one comes from the dam. And that's the fundamental nature of that double helix structure of DNA. And again, we can get way too far down that path, but let's keep it simple. One gene comes from the sire, one gene comes from the dam at every location. And additive genetics simply says that those two, or at that location, the alleles or the genes that can be located at or found at that location have a value. Now, it might be for a weight trait, it might be for something else that can be quantified, but let's think about two different genes that would be possible. And if we say that the A allele has a value of 0 and the B allele has a value of 1, an individual is going to get one of those from its sire, one of its dam, one from its dam, and we simply add up the value of those two genes or two alleles to come up with its genetic value. So if it's an AA, it's a 0. If it's AB, it's a 1. If it's a BB, that's 2. And that's the definition of that additive piece. It's just the addition of the genes from the sire and the dam. Okay, gene combination values are different, and they represent a difference, away from, maybe greater than or less than that additive genetic value. They complicate things a little bit, and we'll talk about some of those complications. But for now, individual gets two genes at every location, one from the sire, one from the dam, and when that individual becomes a parent itself, it only contributes one of those two to its offspring. Okay, so consequently, additive genetics are passed to the next generation, one of the two at random. Gene combination values, which are determined by the difference or the similarity between the two genes that an individual has, gene combination values are not passed to the next generation because an individual only contributes one of the two. Okay, so that tees us up for a definition of heritability, which is important. Heritability, in textbook terms, is the ratio of additive variance, or the proportion of phenotypic variance that's due to additive genetic variance. Or quite simply, heritability is the genetic component that's reliably passed from one generation to the next. Okay, when we think about accuracy of selection, which is ultimately what's going to get us toward our goal, is accurately selecting for the genetics that are going to reliably move our population in the desired direction. There's a couple different types of cartoon hearts that we could find. And if we're making a Valentine, or an anniversary card or something like that for someone special, and we use this realistic cartoon heart that's portrayed here, that's not necessarily going to result in a lot of warm, fuzzy feelings. At the same time, if we're getting a heart transplant, we don't want it to be, we don't want it to be the Hallmark type card heart. We want the real thing. And so when we're selecting for genetics, we want the real thing too. And there's a hierarchy in the average level of accuracy of a selection criterion relative to the additive genetics that contribute to that. Visual appraisal is very important in our sheep world, and yet in terms of selection accuracy and the assessment of additive genetics, as Jeremy alluded to with his diagram there, visual selection is low on the totem pole. If we measure a trait, whether it's a weight or a height, so forth, make it quantitative at least. It's a little bit more objective. We remove some of the guesswork out of that, but there's still a lot of factors that contribute to those measurements. And so many times we see adjusted measurements that account for the age of dam of a lamb or its birth and rearing type. If it's a single, we certainly expect it to be heavier than a twin or a triplet. Sex, we expect rams to be heavier than ewes, and so on and so forth. We can also select for correlated traits, and sometimes, an example being scrotal circumference. If we're evaluating scrotal circumference in rams, that certainly has a lot to do with their semen volume, their serving capacity, but it also has an effect on the daughter's age at puberty and their own reproductive fitness. And so selecting for correlated traits, many times, even though it's indirect, it can allow us to make progress in the trait that's not directly measurable. All of these traits, are so far assessments that are taken on an individual. And if we're really interested in an individual's genetics, and what they're going to pass to the next generation, measuring their offspring, measuring that next generation, or making assessments in that next generation, is going to give us more accurate information in their genetic ability. And so progeny testing, I would put next on the list. This might be a case of taking a couple different rams, splitting a ewe flock in two, and mating each of them to half and comparing the performance of the offspring for any of a number of traits. Now we have the technology to run those rams together to do DNA testing to see, which rams sired the most offspring, and then ultimately who matches up with whom and how they compare as well. But progeny testing is certainly going to get us one step more accurate information on an individual's genetics than that individual's own performance by itself. Next on the list, as Jeremy alluded to, is estimated breeding values, or EBVs. This is what's generated by the National Sheep Improvement Program, as well as really any other large-scale sheep genetic evaluation worldwide. You might see that expressed as EPD rather than EBV. Not going to get too far into the weeds on that, but essentially those are estimates of additive genetics. And an estimated breeding value is one step more accurate of an assessment of an individual's additive genetics than progeny testing, because it includes all information on all related individuals in the database, whether they're progeny or maternal grandsires or whatever the case may be, weighted by their appropriate expected genetic relationship. And it also includes all the information in the database on all the different correlated traits. Okay. Again, that's just based on quantitative information, performance records, so to speak. And now with modern technology, we have the opportunity with some breeds, some traits, and certainly in other species here in the US, to include genomics into those breeding values as well. And so that allows us more opportunity to predict performance before an animal is old enough to express a certain trait, for example. Genomic breeding values do not stand on their own, but they certainly add some degree of accuracy to quantitative estimated breeding values when necessary. So just tying these two themes together, whether you're using the National Sheep Improvement Program, NSIP, or another genetic evaluation, or whether you're simply keeping your own records. An estimated breeding value in its purest form, just thinking about an individual, is the product of the heritability for the trait, because every EBV is for an individual trait, heritability of the trait multiplied by the difference between that individual's performance for the trait and the average of its contemporary group. Contemporary group means same sex, same age, same management. And so if an individual ram weighs 105 pounds and the average of that contemporary group is 100 pounds, the EBV is 5, the difference between 105 and 100, times the heritability for the trait. Okay, and so the greater the heritability, the more important that individual's own performance difference from the average is for its breeding value. EBVs, again, increase selection accuracy by accounting for environmental effects, removing those from the estimates, evaluating genetic effects, and making sure that those that are accounted for are additive in nature. And it weighs information on all records, on all relatives for all traits in the database. Okay, and this is just a list of some traits that are available from NSIP. Not all of these are reported widely in the database, and there are some new ones. But number of lambs born, number of lambs weaned are essentially reproductive traits. Scrotal circumference, also a reproductive trait. Birth weight, weaning weight, post-weaning weight are weight traits. You could add mature size into that as well. Maternal weaning weight is essentially the proxy for milk, milk and maternal. In other words, how much of the of a lamb's weaning weight is attributable not to its growth genetics, but to the maternal environment that its dam provided. Eye muscle depth is loin eye muscle and proxy for muscle size and conformation in the carcass. Back fat thickness, again, a carcass related trait, has some implications for flushing ability and so forth. And worm egg count or fecal egg count is assessment of parasite resistance. Jeremy, anything you wanted to jump in on here?
Yeah, just sort of add a few of the other things that you can track as well. I mean, there's a spot to record dystocia scores or lambing ease type scores. If you record breeding dates, it will help you track gestation length. Obviously, other breeds are tracking fleece traits. And then there's a new genomic EBV study that's happening where we're measuring some other traits that may eventually find their way into NSIP as well, looking at things like body condition score, udder depth, teat placement, FAMACHA scores, mature weights, and so forth. So as Joe mentioned earlier, any trait that you can measure, you could create an EBV for it. And
that's absolutely right. So bringing this back to comparison between those different traits and the heritability focus of this particular talk, working through the definitions we've already given before. Heritability is the proportion of phenotypic variance or the variation in what we see or measure that's attributable to additive genetic variance. If there's one takeaway from the heritability portion of this talk tonight, what I want you to keep in mind is that not all traits are equal in their heritability, and so this is a generalization, but as I show you some specific heritabilities here shortly, they do generally fall into this category with few exceptions. The heritability of survival and reproduction traits is relatively low, often 5–10% range. Growth traits are moderate in heritability, many times in that 20–25% range. And carcass traits are high heritability. That's not generally, or it's generally closer to 0 than it is to 1, or closer to 0% than it is to 100%. But a high heritability, in the neighborhood of 45, or sometimes we even see traits that get into the 55–60% heritable range. That's high heritability, even though it's certainly still far away from 100%. Just to put this in perspective, if we use a heavy muscled ram, that muscle size conformation, however we measure it in assessment or assess it, is reasonably likely to be contributed to the next generation. Whereas at the same time, if that ram gets struck by lightning or gets hit by a bus, his own survival is not very good. But that is not a heritable trait that is very likely at all to be passed to the next generation. It might have something to do with his ability to seek shelter in a lightning storm or whatever, but certainly not as heritable as muscle conformation. Jeremy?
Well, I just say, we've used a few terms that we maybe should have defined a little better at the beginning, but we talk about a lot of these traits in performance traits as being quantitative in nature, and that they are typically controlled by many different gene pairs at many different locations, and it makes it difficult then to measure, compared to traits that are more qualitative, where they're simple, like the horn polled, which is a simple one gene. It either is horned is dominant, polled is recessive, so you get 2 copies, and it's polled, and it's easy to select for, or scrapie resistance, susceptibility, those kind of things. They're more black and white. But our quantitative traits, controlled by many gene pairs. Joe mentioned the additive gene action, but also then you have those environmental influences that make selection a little more challenging.
Yeah, a good rule of thumb, ironically, or unfortunately, however you want to look at it, is that the more important a trait is, generally economically, the more complex its mode of inheritance is. And so that's where this heritability does come into play, because those just because a trait is controlled by many genes does not necessarily mean that it's not highly heritable. There's just different modes of inheritance, and we could go far into the weeds on that, and I'll try to steer it away. But just kind of think about this general categorization: survival reproductive traits are lowly heritable, growth traits moderate, carcass traits high. This table outlines some of those specific traits, again from the sheep production handbook, and hopefully shows me reasonably correct, although you will certainly see some exceptions, scrotal circumference being one of those. Even though it's a reproductive trait, it's in the moderate to high heritability category. Growth traits typically tend to be a little bit higher. Carcass traits are the highest. Wool traits, if we're interested in them, also generally tend to be highly heritable as well. Jeremy?
I just wanted to mention a couple things, and we've touched on this a little bit, but there's also a correlation between traits, and sometimes it's positive and sometimes it's negative. And we talked about, the one fertility trait that's more highly heritable is scrotal circumference. So if you are selecting rams with larger scrotal circumference, you may improve some of those other fertility traits because they are positively correlated, particularly age at puberty in the offspring. Your growth traits tend to all be positively correlated. So if you are selecting for increased weaning weights, you will by default increase birth weights, 60-day weights, 120-day weights, and mature weights. Perhaps not at the same rate, but also along those same lines. You will tend to do that. There's also traits that are negatively correlated. And for example, sheep that have high muscle, high eye muscle depth compared to high growth, those two traits tend to be negatively correlated. So it's difficult to find individuals within a breed that excel both at, say, 90-day weight and large eye muscle depth. So trying to find those outliers that excel at both can be more of a challenge.
And what we're definitely alluding to here, and we will return to it, is that most times it's not just one trait that's important. There are multiple traits that are important, have different weightings, and they're going to have relationships between them. They don't happen in a vacuum. We select for one, it might increase another, or it might decrease another, and that may be a good or bad thing depending on what the trait is. And so we'll bring this back to multi-trait here in a minute, but when we think about making that change in a population, our rate of change or genetic improvement per year for a trait, for a combination of traits that's uniformly weighted. There are things that are going to increase our rate of change, and there are things that are going to decrease our rate of change. Things that increase are in the numerator. The accuracy of selection, how close our criteria are to those actual additive genetics. The intensity of selection. Keeping one ram out of 100 is more intense than keeping one ram out of 2, or keeping 20 rams out of 100. The amount of variation that's present in the population for the trait is important. If there's not variation, we're not likely to be able to change it much. If there's wide variation, which there is for many traits in the Suffolk breed, we have opportunity to move that in many different directions. Each of those things will increase the rate of change. The generation interval, which is the average age of an animal when it becomes a parent, the older that animal is, or the older the flock is, the slower the rate of change. Not necessarily pushing or recommending that we only keep young animals for breeding, because that limits our ability to evaluate things such as longevity. But if we wanted to make rapid genetic change, our youngest animals are the most likely to do that, assuming that our selection criteria are reasonably accurate. Okay, and so we think about designing these programs, and the first practical consideration is what traits are economically important. We can chase a lot of different things, and ultimately, if they don't translate into a value, we can spend a lot of time spinning our wheels or moving in a direction that's not productive. Are the traits measurable? Are we able to quantify them in a way that we can objectively measure progress? What does it cost you to measure them? There are some things that are difficult or cost prohibitive, or difficult to get technicians available to measure certain traits. Weighing that information relative to the value of the information, or the access to getting the measurement relative to the value of the measurement itself, is an important consideration. We can record all kinds of different things, but ultimately, if we don't store it in a way that's accessible and use it in our breeding program, it may not be particularly valuable to us. And ultimately, the reward of that measurement, that intense selection and time spent, needs to be greater than the cost of doing it. But again, if it's variable and it's heritable and you can measure it, you can change it genetically. I alluded to this with Jeremy's last comment, but typically the traits that are most economically important are survival, reproduction, and this is in a commercial system, but also in a purebred system that's trying to make a profit. Followed by growth and followed by composition traits. Now, again, note that economic hierarchy is in the opposite order. of the heritability for the trait. So what that's saying is that some of our most important traits for commercial production are the least heritable. We can certainly select for animals that are only born twins or ewes that have mostly twins, and we can make progress in that over time. But it's certainly going to be slower, than selecting for loin eye size, for example, which is a highly heritable trait. Jeremy?
Just adding a couple of things that are somewhat related. To me, it's interesting that this order that we have here is also the same order in which Mother Nature prioritizes nutritional intake. So the animal eats first to survive, then to reproduce, and finally to grow, and then the composition type traits. And so the other thing that I think we sometimes forget as we try to focus on selecting those animals with genetics for high performance, that those individuals also have a higher nutritional requirement. And if we're in a situation where we don't have adequate feed and management resources then those animals may not express their genetic potential. So just something to kind of keep in mind as a side to this.
Yeah, phenotype is a combination of genetics and environment. And so when we think about a purebred, whether it's a Suffolk or any other breed, that breed is defined by its purpose, but that purpose is relative to a specific environment. Many of the breeds, including the Suffolk, are named for a specific geographic region where they originated, that had very specific feed resources, very specific topography, and we've certainly outgrown that very narrow focus or purpose at this point. But the breed's purpose is generally relative to some specific available resources. And that might vary from one end of the country to the next. It certainly does here. And the Suffolk can fulfill many different purposes. But the contrast between a Suffolk and a Shetland or Icelandic, as shown here, is going to be considerable phenotypically. It's also going to be considerably different relative to their use. And where we might expect a Suffolk to perform exceptionally well in an environment that provides the nutrition necessary to reward that performance, that same level of genetic performance is not going to be efficient, in an environment where a very small-framed, hardy, and high survival sheep, is able to survive, but wouldn't have a lot of performance. In other words, we switch the environment of those two animals, we wouldn't expect them to be efficient. Many times the purpose of a breed, the most important commercial purpose, is to make crossbreds. We'll talk about this, but hybrid vigor is the most powerful tool in animal breeding. It's generally essential for commercial production. And yet our goal and it's our ability to provide that hybrid vigor relies on our maintaining the purity of the Suffolk breed, and maintaining a high level of homozygosity, or genes that are very similar, so that when they're crossed to breeds with different genetics, that hybrid vigor results, and we'll demonstrate that. But that predictability of the breed to fulfill its purpose in a given environment is the overarching most important piece. Within purebreds, that generally entails some level of inbreeding. Inbreeding is just the mating of animals that are related. It comes with a negative connotation, and there's some reasons for that. But all animals within a breed or within a subpopulation are inbred to some extent. It's just a matter of the difference in the closeness of that inbreeding. At the genetic level, that inbreeding results in more genes that are similar, or a higher probability that those genes are identical by descent. And inbreeding, to a point, is essential in a purebred to be able to stamp characteristics that we ask that breed to stamp. And generally, it's a liability or an undesirable thing in crossbreeding, commercial production. One more thing that I'd like to bring up about inbreeding, we could spend a whole lecture on this one too, but inbreeding does not cause genetic mutations. It simply allows genetic mutations that exist within the population, if they're recessive in nature, to double up and express themselves. And so in some ways, the best safeguard against the challenges of inbreeding that come from genetic defects is to inbreed to some extent and be able to identify them. Again, we're scratching the surface on something that we could spend a lot of time on, but generally, inbreeding is important within a purebred to a certain level to be able to guarantee predictability for the purpose that they're used for. Jeremy?
Yeah, just to add a couple things, just sort of tongue in cheek. I tell people, if it works, it's called line breeding, and if it doesn't, it's called inbreeding. But that's not exactly true. But there are reasons why you would do it, and Joe kind of touched on those to kind of maintain the integrity of your breed. I mean, that's how breeds were first established, to get consistency in appearance and everything else. But there may be cases where if you have an elite seed stock flock, you just simply might not be able to find better genetics in another flock to bring in. And so you're forced to kind of use your own genetics. As Joe mentioned, you will increase your consistency because you sort of get more homozygous gene pairs. Now that, as Joe mentioned, there can be some negative effects. You will lose a little bit of diversity. You can reduce fertility if inbreeding gets too high. And as we mentioned, the potential to express those recessives if they are in the population. But I think sometimes people try too hard to avoid it. When it can be helpful in some situations.
For sure, and different traits are going to respond differently to inbreeding too, and that has a lot to do with their with their heritability and their response to heterosis, which we'll show here in a minute. Just thinking about multiple traits, single trait selection is very seldom ever a good strategy. It's important to balance that selection for multiple traits. That needs to be done with the understanding that there are often relationships or antagonisms between traits that are important. And so selection for one trait might result in undesirables in another. A Beltex, is shown on the left here, has more muscle shape than a fin sheep, but it's not nearly going to be able to combine or to compete with that fin for prolificacy or lambing ease. And there are some strategies to overcome that, but for now, the take home is that those antagonisms between traits are the reason why we have breeds that are specialized for specific purposes. In the cattle world, why we have beef cattle versus dairy cattle. In poultry, why we have broiler strains versus layer strains of chickens. Or in swine, terminal and maternal lines, because the genes that are responsible for those traits are antagonistic. Also, the more traits we consider in a breeding program, and the more balanced those selection criteria are, the slower we would expect to change the population. The more complex we make the selection criteria, the slower the rate of change. Not necessarily always a bad thing, but a consideration to keep in mind. And so in the genetic evaluation side, this is often evaluated with a selection index, which combines different traits, many times, or most times measured by EBVs or some form of estimated breeding value. And they have a relative emphasis in that index. Again, this is not a gold standard, just an example, of a genetic index identified for us, Australia, and developed as a desired gains index, which changes the different traits in the population in in a targeted direction for a specific population and a specific industry with economic or market demands on it. Jeremy?
But just the indexes, NSIP has a couple of them built in. The Suffolk breed, we have a carcass plus index that kind of combines growth and muscling and a little bit on the back fat. The maternal breeds, there's like a Western range index and different things like that are built in. But you can also kind of create your own by identifying, as Joe said, those traits that are important in your flock and figuring out a way to weight each of those and come up with your index.
So bringing this back to the animal breeding example we've been walking through, we talked about the concept of heritability, and the other one that complements that is the response to heterosis, or hybrid vigor, as many people are familiar with. We worked through the example that we've been using. Phenotype is genotype plus environment. Genetics are additive and gene combination values. Heritability pertains to that additive genetic variance. Okay. Generally, survival and reproduction traits are low, carcass traits are moderate, or carcass traits are high, growth traits are in the middle. For heritability, the response to heterosis is opposite. And the reason why that is because heterosis, by definition, is a gene combination value. And those things, additive genetics and gene combination values, are relative percentages, and when one increases, the other decreases. And so the response to heterosis for these traits move in the opposite direction. So the take home here is that if we're in a commercial scenario, or even within a purebred scenario, if we are trying to improve a trait that falls within that survival reproduction category, generally selection for a phenotype in and of itself is going to be relatively slow in the rate of progress. And we will make more rapid progress in improving that trait by harnessing hybrid vigor or heterosis. Now, common misconception, heterosis does not necessarily require two different breeds. There are heterosis effects that can happen within breeds. Certainly the Suffolk breed, as diverse as it is, there's a lot of different genetics, diversity of genetics that when combined can have a high heterosis effect. We select and expect to make the most progress by selecting for carcass traits, highly heritable carcass traits, or highly heritable traits. When trying to improve a lowly heritable trait, will make more progress by crossbreeding or managing inbreeding or managing the environment. Okay, and so understanding the difference between the heritabilities for the traits, how that contrasts to how they respond to heterosis, and ultimately how to measure or how to improve them in a breeding scenario is important. Again, not all traits are created equal. Jeremy?
Yeah, so I just want to kind of give an example of one of those. Like, we all, raising sheep, we all know the more lambs that we get that survive, the better off we are economically. But we also, as we showed in the chart, that lambing percentage is a relatively low heritability trait. Now, there's a few breeds that have a separate gene for fertility, Polypay-Finn, Romanov, Barula, maybe a few others like that, but that allow them to produce litters of lambs. But Suffolks and most other breeds don't have that. So you're looking at 10% heritability. And so if you select and select and select twins and twins and triplets, you'll make very, very slow progress. But keep in mind, 10% heritability then means about 90% is environmental factors. Those are things that you actually can control, some of them. And so if you want to increase your lamb crop percentage, better nutrition, flushing, nutrition throughout gestation and lactation, controlling parasites and other health challenges, and even utilizing the Suffolk's natural tendency to be more fertile a little bit later in the breeding season. There was a study done just simply moving the start of your breeding season from August back to September you can increase lambing percent by like 15%. And that's typically due to the heat of August that causes embryo loss. And so if you skip that, you'll have more twins and triplets. And so just a different way to, we focus a lot on genetics, but you can also manage environment to improve some of these traits.
So the path to improving any trait is going to be dependent on the heritability for that trait, plain and simple. Just a diagram to show us the pictorially what I mean by heterosis. Heterosis simply means that the crossbred animal between two different breeds performs differently than the average of the parents. Usually that's greater, or usually it's in a more desirable direction. So in this case, that heterosis effect would be represented by the purple portion of the middle bar, where the green is the quantitative average between breed 1 and breed 2. The purple says that individual is going to perform greater than average. Again, heterosis can occur within purebreds. And so, for example, if you're having a fertility challenge, sometimes it simply means that an outcross is needed, or a little different genetics to shake that up. In the remaining time that we have here, just an example of the additive heterosis effects in a crossbred ewe. Now, this is obviously not a direct Suffolk example, but demonstrates the power of this tool. The relative percentage increase of that heterosis effect, is shown for the different, many times economically important traits listed here. And if we sum them up, essentially the weight of lamb weaned per ewe exposed, the bottom line, weight of lamb weaned per ewe exposed, can be increased by 18% simply by the fact that that ewe is crossbred. Now, that's 18% greater than the average of the parents. And so if the parents are no good, it's still not necessarily going to mean that the crossbred is any good, but it's going to be better than the average of the two. And so more directly relevant Suffolk example, when we think about a terminal sire, that weight of lamb weaned per ewe exposed from the fact that the lamb is crossbred can be increased by 18% just by being crossbred. Now, certainly there's going to be some additive genes that we would expect to come from the Suffolk side as well, and pull that average in the desirable direction. But the bottom line is that 18% is as close to a free lunch as we're going to get. The inputs don't increase to the same proportion that heterosis benefits. And so crossbreeding is the most powerful tool in animal breeding. At this point, it should be becoming obvious that mating decisions are critically important, and in many cases more important than simple selection. And so designing mating systems, we've mentioned terminal breeds, maternal breeds. The two things that a valuable mating system needs to or should capitalize on are heterosis and breed complementarity. If it's within a purebred, again, understanding that the likelihood or the possibility of that heterosis effect happening within purebreds, and the complementarity between the two types to hopefully balance out on some type of optimum, is going to be important. And so breeds are classified based on the trait strengths that they can add to that system. There are a ton of different mating systems. This is a whole other conversation at the commercial level, but using two breeds in rotation, I managed a flock in New York years ago that used old school Suffolks and Dorsets in rotation. Suffolk sired ewe lambs got mated with Dorsets and vice versa. 3-breed rotation, same thing, just with 3 breeds. Various terminal crossing systems where all the offspring of those terminals go to market, including ewe lambs. Ultimately, we need to think about our end product, the most efficient way to produce that, and how to capitalize on the selection advantages of highly heritable traits and the heterosis advantage of lowly heritable traits that benefit when we put different types of sheep together. And so an example that that I like to use, I'm not necessarily condoning this for for the U.S. sheep industry, because there are some exceptions in different parts of our country that don't necessarily make this applicable. But the genetic principles at work, I think, are a good model, not only for sheep breeding, but for animal breeding of many different species. And so in the UK, essentially different levels of topography, resources, and at the very top, extremely harsh environments, very rocky, very challenging to access, not valuable for much of anything aside from grazing sheep. And so the sheep that can thrive in that environment or survive in that environment, called hill sheep, they're hardy, they're tough, they are fertile, but they don't have a lot of prolificacy. They typically have singles. They don't have a lot of growth or milk production. Their production is in line with the limited resources available in that challenging environment. Okay, moving through this hill sheep kept pure in that environment, and lambs are marketed off of them at the end of their productive life. A ewe probably around 6 years, she's going to be drafted off of the hill, moved down into a more feed-intensive environment, where she's given a little bit more care and not asked to survive in that challenging environment. She's still got some life left. Mated to a maternal crossing sire, in this case a blue-faced Leicester, and the ewe lambs from that cross are referred to as mule sheep. They bring a lot of hybrid vigor to the table, being F1 crosses, first generation crosses. They retain a lot of the hardiness of the hill dam, but add a little bit more prolificacy, milk production, growth, and extension from the maternal crossing sire. And those mule ewes, which vary a little bit depending on the breed of hill sheep, are the most common commercial breed of sheep in the UK. Those mule ewes are then moved to lowland environment, again, very intense or more intense feed resources, mated to terminal sires such as the British Suffolk shown here. And the product of that cross is completely terminal. Those lambs benefit from, on the heterosis side, the individual heterosis of having a terminal breed sire and a maternal crossbreed dam. The maternal heterosis from the fact that their dam is crossbred, and the complementarity of additive genetics, where the Suffolk is highly selected for muscle and highly selected for growth. And those two things, those traits combine exceptionally well, match these sheep to the environments that they're thrived in, harness heterosis and breed complementarity. And that picture in the bottom right represents the majority of commercial crossbred lambs in the UK. Now, they're experimenting with different breeds. There's a lot more composite breeds and variations from this system. It's not all done this way, but the principles apply. And so that's a commercial application of these principles, but we back it up within a Suffolk flock. Again, our goal ultimately should be to provide this kind of service to the commercial sheep industry, which ultimately is what's going to keep our breed thriving as well. And so understanding the difference between the traits and their heritabilities, how to combine them, is pretty critical. I've run a few minutes over time, and so I better stop it with that and open it up to any questions that anyone has.
Again, for anybody who is joining us, you can share your questions through the question and answer chat window on Facebook. You can share those through the comments. While we see if any questions come in for both Jeremy and Joe, a question from the office, we have a lot of members who sell rams as terminal sires, and there's always a lot of questions about from buyers of those Suffolk bucks if they are twins or triplets. Can you talk a little bit about heritability of multiple births and maybe how members can talk to their customers about that when they're having sales of their rams off the farm?
Sure. So the bottom line is that heritability of prolificacy, or number of lambs born, is low. So even if we are selecting females within our own flock, and only keeping twins, discounting singles, discounting triplets, a lot of what the overwhelming majority of what we're selecting for in that phenotype is environmental or non-additive genetics. And so our progress is going to be relatively slow. In a terminal sire situation where none of the ewe lambs are retained for breeding, the relevance of that sire's breed or birth type, single, twin, triplet, etc., is zero. Okay, that sire, whether he's a single or a twin, has no bearing on what the commercial ewes that he's bred to, what their fertility will be.
Yeah, that's a great point, Joe. And I think for years, that's what people have asked. They asked that question, and it really, we're asking the wrong question there, because those rams, unless there's some kind of challenge to them, they're producing about 9 billion sperm cells every time. So they have no influence over how many lambs, especially in that terminal situation. So it's the ewes that determine that in the environment that they're raised in. So while people may want it and may ask for it, as Joe said, it really has almost no relevance, and it really has zero relevance in a terminal situation.
The fertility of a terminal sire is critically important. I'm not going to say that it's not, but that doesn't affect the difference between 1 and 3 lambs. It affects the difference between lambs and no lambs.
Correct.
No other questions? We're getting a break tonight.
Sorry. I was talking and I was on mute. For anybody who's on, looks like we have a question that came in. I can read it to you. I understand breeding terminal sires to maternal ewes in commercial system, but as a purebred breeder of a terminal breed, how much selection should there be for maternal traits? We want productive ewes.
Absolutely, a great point. And so there's no magic answer for that, because everybody's feed resources, everybody's labor resources are going to be a little bit different. But the bottom line is that if your terminal sires mothers don't work for you, if they're not profitable for you, you're not going to be able to be in business. And so there has to be enough maternal performance to be able to be viable as a Suffolk breed, irrespective of any of the uses of the Suffolk breed commercially. Bearing in mind, however, that terminal traits and maternal traits tend to be relatively antagonistic. And so the more we try to balance between terminal and maternal traits, the more limited our progress in any one of those directions is going to be. So the balance is going to be different for everybody, and it comes down to available resources and what works in your own system, as well as what works for your buyers. And that feels a little bit like I'm evading the question, but the truth is that it depends.
Yeah. Well, and I would just add to that, Joe, just as we talked about earlier, keep in mind that so many of our reproductive traits are are relatively low in heritability. And so, you're not going to make a lot of progress selecting for them. And so you kind of use it, I guess I would say you use it as a default. If you have ewes that just aren't good mothers, for instance, that's a little bit more of a subjective measurement, but things like that you can call for to get rid of some of those issues. We're looking at some other traits with udder conformation and teat placement that may help you stay productive in the flock longer, but that's still relatively new. We did talk about scrotal circumference, and that is one area where we should all be paying attention to in our rams, and it will have a positive effect on some of the other fertility traits in our flock if we're keeping daughters out of them as well. So.
And maybe a little bit of a tangent, but just a thought that crossed my mind as you were saying that, the reproductive traits that we would select for and that would be strong in a Suffolk flock that's highly selected for maternal traits. There's going to be correlations between maternal fertility and performance and male performance and fertility. However, when we translate that from a purebred scenario to a commercial scenario, many times, we attribute things that are lack of fitness or lack of fertility in a commercial scenario. We attribute that to genetics, where there is a genetic component, but it's a lowly heritable trait, and we can make a lot of progress simply by managing the environment of those bucks, conditioning them, giving them exercise, hardening them up on less than soft feed, and by managing their environment for them to be able to thrive reproductively. And so, taking that again to the commercial level, we can often misattribute things to genetics that are really simply a matter of management.
Okay, I don't see any other questions. For those of you who are joining us, this will be archived on the Suffolk Association website, suffolks.org. Slides will both be posted as well for you to go back if there's some tables that were shown during the presentation that you'd like to look at again more closely. Thank you so much for everybody joining us tonight. Thank you to our speakers, and hope everyone has a great evening.
Thanks, Amanda.
Thanks a lot.